the Sheldon Shi. He will discuss new results from electron-positron heavy flavor factors. Thank you.
Okay. So, hello everyone. It is my great honor and pleasure to speak here and talk about the new results from electron-positron heavy flavor factories. Let me begin with the big picture. As we all know, the standard model as a quite successful theory still remains many big questions unanswered. For example, it doesn't account for the matter and antimatter asymmetry, the dark matter, dark energy, extra, and also as a theory, it cannot explain why there are several hierarchies and extra. So all of those points towards to the new physics, but yet we don't know where the new physics is hiding. From collider experience, there's two complementary paths to search for new physics. The first one is energy frontier, where people can search for the new particles directly. The second one, as the flavor frontier, where we can search for the new physics or the new particle by their virtual effects. The second approach has been approved quite successful and powerful. In the history, we anticipated the charm quark and top quark before we found them. So, and it is remain true today, as shown in the red plot. From the flavor observables, we could set quite high constraints on the new physics energy scales, which is far beyond the level we can reach from the energy frontier. By the way, to have a reliable constraint on the new physics energy frontier, by the way, to have the quite reliable constraints on the new physics scales, we need a better understanding on the QCDs. So this morning we heard from Patrick that excellent progress from LCB, which is a flavor factory on hadron colliders. So when we wonder why do we need electron-positron colliders for the flavor physics, let me answer this question with these advantages. The first remarkable one is the collision environment is quite clean, as we can see from the right. The average number of trucks or showers per event is only 10 or less. And we also have quite excellent reconstruction for the neutral particles, the gamma or the pi zero. Also, we know the initial energies quite well from the collision of the electron-positron, so we can perform quite excellent missing energy measurements. Another unique feature is from electron-positron collider, we always could have the quantum coherent Meson pairs, B0 bar, D0 bar. With this, we can perform the measurements which are quite hard or even impossible anywhere else. So yes, electron-positron flavor factories are quite complementary to LHC. The main players in this string tree are the following. We have the Barber at Slack and Bell at KK as the first generation of B factories. Then Bell 2 as the second generation of B factory has recently accumulated almost 1 university bar data. Actually, from these curves, we can see, especially in this year, the operation of the Bell 2 and the Super B is quite stable. We could reach averagely 3 inputs per hour per day. And another milestone of Bell 2 is we surpassed the Bell's through 4S dataset, which could enable us to do more precise B Meson decays. And another flavor factory is Space 3 as a unique Tau-Chang factory. With 17 years running, Battery has collected a comprehensive spatial Tau-Chang data sample. All these flavor factories enable us to cover quite a broad range of physics topics from B mesons to the Tau and the charm. And at this conference alone, from the parallel sessions, there are 34 physics talks from this four experience. So naturally, I cannot cover all of them, but instead, I will only highlight you some. I will only show you some highlights covering these three directions: anomalies, seeking metrics, and the QCD. So first, with B anomalies, which can broadly divided into two categories. The first one involves charge current transitions. For example, B2S new bar as error, and the second one involves charge current transitions. Well, for the first one, 3 years ago, Bell2 reported the anomaly into B2K new, which has found to have a higher branch fraction than the standard prediction. The tension is about 2.7 sigma. And recently, we did a reinterpretation of this result in terms of the Wilson coefficients. And also, we released all the full likelihood and joint number density to this community. So even you are not a Bell2 member, you'll be able to test your preferred new physics standard model on the data. And we have gone further. We are investigating this anomaly from many aspects: K tau tau, K access new bright, access error. And regarding the second type, the charge current transition, it is about the famous RD star anomaly. Well, in the standard model, we know that the W boson couples equally to the 3 generations of leptons apart from their mass. Well, new physics may not. So this is called the lepton flavor universality test. Always, we test this by the ratios because many uncertainties can be cancelled out. And from experimental side, it is quite challenging because there's many missing neutrinos in the final states. So what we do on the electron positron colliders, we could first attack one beam mechanism using either harmonic decay or the semi-leptonic decay. Then we can search for our signal from the tracks and the showers in the rest of the event. In the past, there are already many results from the Barbara, Bell2, and the RCB, which are summarized in the red plot. The experimental average is found to have tension with standard model at around 3 sigma level. So this plot is the status in last September, and let's see in the recent 10 months what we have from Bell2 and Barbara. From Bell2, we reported the new RD star results using the harmonic tag and using the tau to pi new, tau to rho new decays. Equally important, we also measure the polarization of the tau leptons because with this new extra observable, we could be able to know which new physics current contributed to this anomaly. The result is based on round 1 Bell2 data sample, and the result is found to be consistent with standard model and the previous measurement results. The second one is from Barbara, which is more interesting, using the semi-leptonic tag, which is statistically independent from previous Barbara's results. They are trying to identify the signal from a large fraction of the background events. So they train 2 MV classifiers to merit, and the result is found to consistent with standard model at 1.5 sigma level. So with these 2 new results, let's see where do we stand today on this anomaly. Here's the new summary plot, and we can see the experimental results move close to the standard model prediction, and the tension now is only 2 sigma, but we should notice that now for the new average, the p-value is very poor. It's only 1%. It was 27% before. And this 2 sigma doesn't mean this anomaly has gone or not. Well, Bell2 and the RCB are accumulating much more data in the near future. We could expect this picture will keep evolving, as well as we understand the background much better than before. Now let's move to the second part, which is CKM metrics. It is a fundamental part of standard model and flavor physics. So this CKM matrix covers all the quark flavor changing transitions, and it provides the only one CP variation source in the standard model from quark sector. And the integrity provides a quite powerful test, which triggers many flavor measurements. So we can basically test it by using the size and the phase of the CKM elements, which is always visualized as the famous CKM triangle. And we also could only rely on the size of the CKM elements. So for the scheme triangle, there's one recent highlight from Bell 2, which is about the apex of this triangle, the alpha angle. The alpha angle remains the least measured angle among these three angles, and we need to do the isospin analysis in the pi system or rule system, which requires the branching fraction and all the CP symmetry of all the final states. However, in the pi system, for a long time, there's no measured results of the mixing-induced CP symmetry as pi 0, pi 0. The reason is simple. To measure it, we need to both B-Mason's vertex information to perform the time-dependent CP relation. Well, we know that for pi 0, pi 0 is almost impossible. However, this is the traditional method, and here it comes the novel ideas. So, what if we only using the decay time of the tag B, could we still get the information of the signal B? It sounds like magic, but it turns out we can. And the physics reason behind it is also the unique feature of the electron pulsing collider, because the B0, B0 pair are quantum entangled at our Bell and Bell 2 and also bar. However, we found that this method, this T-tag method, is only feasible at Bell 2, but not really at bar or Bell, because thanks to two analysis features. The first one is nano beams provided by the super KKB, which can help us to constrain the projection points of the B-Masons. And the second one is the pixel detector of Bell 2, which can provide a better vertex resolution than the previous first generation of B factories. And with this novel method and the advanced machine, let's see the results from Bell 2. From the round 1 sample, we only found around 170 signals. Still, we could perform the first mixing-induced CP relation, the S pi 0, pi 0. And although the uncertainty is a bit large, it's about 0.7, 0.8, but we already see it is quite powerful on the constraint of alpha. And as we can see from the red plot, the 1 sigma interval was reduced by 40%, and the 2 meter solutions are dropped. So with innovative method and advanced technology, we are turning the impossible into precision measurements. Speaking of precision measurements, Bell3 delivers quite precise VC as and VCD from the D2 pi RNA and the D2 P RNA. Both of those has achieved sub-percent precision level. And also for these uncertainties, majority of them are actually not from the measurement, but from the external input from the form factor from latex QCD. So to achieve more precise flavor physics results, we need better standing on the QCD. This brings us to my third part on the QCD. So not a surprising thing, on the flavor factories, we can also do the QCD physics quite well. And non-perturbative QCD is quite complex, and the hadron spectroscopy is found to be a quite powerful tool to understand it. Another unique feature of electron pulsing collider is we can tune the beam width energy quite well, which is called energy scan data sample. And both from Bell 2 and Bell 3, we could be able to have quite unique data sample to study the tronium and the plutonium physics. Additionally, Bell 3 has accumulated 10 billion GSI events quite clean and allow us to study the exotic status. So for this ICHEP, there's a new result from Bell 2, which is about the conventional hadrons, the plutonium. For the D-wave plutoniums, for a long time, only the middle one was observed, and recently Bell 2 using the Upsilon 5S data sample reported the first evidence of 2 missing plutonium states through the E plus inverse to the Upsilon eta and the Upsilon pi pi decays. these two new theories enable us to do the first test of QCD predictions on the through 1D mass split links, as shown in the red plot. Another new result is from batch 3, maybe it's more interesting and important, which is about the unconventional hadrons. In the past 20 years, there are many exotic hadrons, the tundra extra. However, there's one obvious prediction from QCD is not confirmed, which consists of 0 charge quark, the globals. So here the story is about X2370. And since it was found 15 years ago, the mass is found to be consistent with the prediction for the pseudoscalar global. Then a comprehensive study was performed on batch 3. Here I flash out the results. The spin parity was determined as 0 minus plus, which means it is a pseudoscalar. And to know, and by checking the inverse mass on the K star K, there's no clear signal for this particle, which means this particle is flavor singlet, as global should be. And furthermore, we found this particle in many decay channels, the pi eta, eta prime, kk eta, eta prime, and kk pi. So for these 5 channels, those are also the golden channel of the ETC decay, which means this particle has quite a similar decay pattern to the ETC. By calculating the Bragg fractions, we find the decay pattern widths of each channel are quite similar and quite narrow. And to identify how much Q-bar content for this particle, we check it. We check the channel of GFZ to gamma gamma phi and gamma gamma omega. From the spectrum of the gamma phi or gamma omega, there's no evidence for this signal for this particle, which indicates that the Q-bar content is quite tiny for this particle. So for all these results from the data, we find the other hypotheses are hardly explained them all, but the global could. So the latest pseudoscalar global should be the dominant constituent for this X2370. Of course, 2 days later, there will be a dedicated talk by Shen Jin, so please join this talk if you have interest. Before my concluding, I want to look ahead. Now BL2 entered the inverse bar area, and we expect a multi-inverse bar at 2032. Well, our ultimate goal is still 15 inverse bar. And well, as for the charm factory, batch 3 will collect more data for the charmed baryon study, for example, the LAMP-C and the KCC study with our greater version of BPC2. So let me summarize my talk. A rich and diverse physics program is ongoing at the Electron Positron Flavor Factories. And here I highlight to you at these 3 directions, the precision results on the anomalies of the star and also the VCD and VCS. And we have performed the first ever measurement on the mixing-induced pi0 from BL2 with a novel idea and advanced machine. And also on the QCD, BL2 and batch 3 will continue to advance our understanding on the QCD. And this is just beginning. The best is yet to come. BL2 has now surpassed the Upsilon-Fries data sample over Bell, and batch 3 will continue with unprecedented Tau Chang samples. With this, I can thank you for your attention. Obrigado.
Thank you, Sheldon. So now I have time for a couple of questions. So maybe I can start with one question about the Apex result you showed about pi0, pi0.
Yes.
Do you know what is what is the efficiency of this this reconstruction? Do you know by?
I don't have the number on top of my head, but sorry.
Okay, because I was wondering, it must be not very good, but okay.
Well, because we have huge background from QQ bar, so we need to.
So the efficiency is around 15%.
15, okay.
Yes.
Thank you.
Thank you, Diego.
Another question? If last chance. If not, let's thank Sheldon again for the nice talk.
Okay, hello everyone. So good afternoon. I'm Farinaldo. I'm actually based here in Natal at the International Institute of Physics, and it's quite a pleasure for me to host Alejandro Ibarra. He'll give us review on dark matter theory. And this is the last one.
All right. All right.
All right. Thanks so much.
I don't think I need this one. So. All right. Thank you, Farinaldo. Can you hear me?
No. Speak. Speak up.
Can you hear? Yeah. Ooh. All right. So thank you, Farinaldo, for the introduction. Thank you to the organizers for the great opportunity to be here in Natal. And yeah, so I was assigned the difficult task of reviewing the theory of dark matter in 20-25 minutes. And let's start because there is a lot of material to cover. So first of all, it is well known by all of you that there is evidence of dark matter in a wide range of distance scales. First of all, in galaxies for the galaxy rotation curves. Secondly, from cluster of galaxies, from the motion of the galaxies inside of the cluster, and also from gravitational lensing. And then finally, also from the cosmic microwave background radiation and from the large-scale structure. So at the moment, there is no evidence of dark matter at the scales below 100 parsec or so, and in particular, there is no evidence of dark matter inside of the solar system, which is something which is critical for some of the search strategies that people are pursuing in the present time. Okay, so for us, a very important number is the dark matter density in the universe, which is about 10 to the minus 6 GeV per cubic centimeter. And then this number already offers us a way to classify all the possibilities for the dark matter models. So if the density is equal to 10 to the minus 6 GeV per cubic centimeter, the mass density is the number density multiplied by the mass. And then you can have candidates which are very, very light with a mass of 10 to the minus 20 electron volts that correspond to a number density of 10 to the 29 particles per cubic meter. So with this large number of particles in this cubic meter, this means you have a large occupation number, or conversely, this means that you have like a classical field. It's no longer described by number of particles, but it's more like a classical field. For many of the people in this audience, we like the GeV scale, that is the scale of many of our particles in the standard model. So for a mass of 1 GeV, then the number density is 1 particle per cubic meter. So this is actually quanta in the universe. So this is the realm of particle physics. And finally, if you postulate or if you accept that the dark matter objects will be very heavy with a mass of 1 solar mass, then the number density is this ridiculously small number, 10 to the minus 57 per cubic meter. Maybe to put it in more reasonable units, corresponds to 30 dark matter objects in a cube of a size of 1 kiloparsec. Okay? So this is the different realms, the ultralight dark matter, the wave dark matter, classical fields, the particle regime, and lastly, the regime where dark matter is made of macroscopic objects. So in my talk, I'm going to review a little bit these different candidates and tell you some of the recent developments in each of them. So let me start with the wave-like dark matter. So the first thing to note is that these objects, being so light, they have a huge de Broglie length of the kiloparsec, and this already tells you that this gas is going to be classical, the wave functions are overlapping, and moreover, it gives you like a lower limit on the size of these objects because you have to fit this ultra dark matter inside a dwarf galaxy that has a size of 100 parsec. So from the particle physics viewpoint, this dark matter field, that here I suppose that it is a pseudoscalar, couples to the F dual term with the coupling constant, which is dimensionful with units of mass to the power of -1. And this action field is still oscillating at present times with a frequency that can be as long as years, days, or 100 years, depending on what is the mass. So now here the idea is that this field is classical, it couples a automatic field, and is oscillating with a long, long period. And this is what provides eventually the different methods for detecting these ultralight dark matter particles. So here it is one of the most important constraints coming from this quasar. So this action photon conversion induces like a time variability of the photon flux because because this conversion is time dependent. And the non-observation of this time variation of the flux gives you this limit. So here we have limits coming from the polarization data or the Planck experiments, because of course these couplings will affect the polarization of the mu photons when they traverse this medium of ultralight dark matter particles. Okay, so in this framework of the wave-like dark matter, actions play an important role. They are motivated by the solution of the strong CP problem. And different models of cosmology, of action production in the early universe, favor the mass range between 10 microelectron-volt and 100 microelectron-volt. This is, the battery is finished, I think. But I can continue without it, doesn't matter. Yeah. And yeah, so if this is the case, that the mass is in this mass range, this means that the frequency is about 1 gigahertz or a few gigahertz. And now here the search strategy consists in having a resonant cavity and then to adjust the frequency of the cavity to resonate with this axion resonance. So the increase in the energy of the cavity will give you a possibility to detect or to constrain the existence of this, thank you, Fernando, the existence of these light actions. So what is interesting about this detection strategy is that in the last 3, 4, 5 years, different experiments are starting to cover the region which is favored by models of action dark matter. So this means that there's a possibility of detecting action dark matter in the next few years because there are new experiments, such as MADMAX, that also aim to cover this region here. Okay, so now let me turn to macroscopic dark matter. So here is a model-independent search strategy, which is to look for the microlensing when this dark object passes in between the line of sight between us and some distant star. Yeah? So when the object is in the line of sight, this produces an increase in the luminosity of this star, in the light emission of this star, and that is the signal for these massive compact halo objects. These are the latest limits from the Ogle collaboration combined with the HAC limits. And then what you can see from this figure is that this possibility of macroscopic dark matter is ruled out as 100% of dark matter if the mass is between 10 to the -9 and 10 to the 4 solar masses. From the high energy physics standpoint, there are a few interesting candidates. The most prominent one are primordial black holes, which are produced when the density perturbations enter the horizon. And this is the current status of the searches for primordial black holes. So this plot is very busy. So here you have to concentrate in this part of the planetary space, which is ruled out because of the Hawking radiation, and then this part of the planetary space, which is ruled out by the model-independent limits of macro searches that I showed before. So there is this window, which is allowed between 10 to the 17 and 10 to the 22 grams. That corresponds to mass of an asteroid. But it is interesting that there are different proposals, in particular this one with the GRB, with the lensing of gamma ray bursts, that aim also to cover this region of the planetary space. Okay? Also, something that one should note is that this planetary space assumes that all primordial black holes have the same mass. But it has been pointed out that this is quite unlikely from the physical point of view, and instead you will have a distribution in the mass of primordial black holes that follows like a log normal distribution with these widths. So when you have a primordial power spectrum that is perfectly monoenergetic, which is very contrived theoretically, then you have this window which is open, But when you have this multi power spectrum, which is a bit broader, this also gives you this mass distribution, which is broader, then some of these black holes will end in the region that can be probed by Hawking radiation, and then some of the black holes will be in the region that are excluded by the macho searches. And then you see that when you have a spread distribution, then this window of asteroid mass becomes narrower and narrower and could be even excluded. But nevertheless, there are going to be new experiments where this region here, which is a sweet spot for macho searches from other black holes, will be covered. Okay, so second interesting candidates are compact dark stars. This assumes a candidate for dark matter, which is called asymmetric, and has strong interaction, so it is very similar to the protons. The protons are more protons than the protons in the universe, and protons have strong interactions. Protons form dark stars, so this means that this object will also form, protons form stars, this object will form dark stars. So in this case, by solving the coupled-Klein-Gordon equation in Kerbal space-time with the Einstein equation, one obtains these distributions that already tell you that the mass of this object, or that the size of this object, will be around 1 kilometer, and with densities that can be 10 to the 20 kilograms per cubic meter, which is comparable to the density inside of neutron stars. So this is the object. So the way to search this object is exactly like a macho. It would be also via lensing. But in some models, it could happen that this dark matter particle interacts with the proton. The proton will collide with the dark star. The proton will be captured, and the proton will thermalize with the dark star and will start emitting radiation. And it could happen, depending on what is the values of the coupling constants, etc., that the luminosity in photons of this dark star could be as large as 1, 10, or even 10 to the 4 solar luminosities. That would be also a way to detect these objects via the correlated detection of gamma ray emission from compact objects, and also the observation of lensing. Okay, so in the last 10 minutes, I would like to concentrate on particle dark matter. Here, the parameter space is much, much richer. So here, one has the dark matter mass, one has the transition cross-section into standard model particles, one has the decay width, the self-coupling, and the scattering cross-section with standard model particles. And there are different techniques to probe these different axes of the parameter space. The detection probes the scattering cross-section. The indirect detection probes the transition cross-section. Also, the indirect detection probes the decay width. And the self-coupling can be tested with structure formation. Okay. So traditional dark matter searches were optimized to detect the lightest neutralino, or the minimal supersymmetric standard model. This means particle which is totally stable with no self-couplings and that interact with everything and annihilate into everything. But in particular, scatters with light quarks, with the valence quarks, and also annihilates into quarks, producing lots of gamma rays. But in more modern approaches, we prefer to be more agnostic, and we just adopt a dark matter scenario, not really a model, but a scenario, where dark matter annihilates to some standard model particle, and dark matter scatters with some standard model particle. Okay? And now here the idea is to identify signals that can give us information about dark matter, and that allow us to explore as much parameters as possible in this 5-dimensional parameter space, which is, of course, quite difficult to probe. So this is the philosophy that no stone must be left unturned in the search. All right, let me discuss what are the results in indirect dark matter searches. So this is the sketch of the indirect detection. One has dark matter particles that annihilate, producing some of the particles in the final state. The neutral particles propagate in straight lines, and the charged particles propagate in a complicated way in the galaxy before reaching the Earth. So photons are kind of a privileged messenger, because this allows us to have directional information of where is this photon coming from. And this also allows to identify different targets. And these are some of the prominent targets. The most important one is the galactic center, but also here it suffers large backgrounds. And for this reason, also dwarf spheroidal galaxies are considered like a prime target for dark matter detection. So for the rest of our galaxies, the Fermi collaboration has taken a sample of different galaxies which are far away from the disk to avoid this contamination from the galactic disk, and these are the limits that they have obtained. Okay? So for the tau-tau and Ericsson channel. So it is quite remarkable because for the first time it is possible to cross this barrier of 3 times 10 to the minus 26, which is the cross-section which is favored by the dark matter freeze-out mechanism. So similarly, for the galactic center, also it has been possible to cross this magic number of 10 to the minus 26. Also, this one is a bit uncertain because of all the different modeling of the backgrounds that you have in the galactic center. But nevertheless, it is important to note that now there is, for the first time, a discovery potential of dark matter both in those galaxies and in the galactic center. Okay, so the estimation for antimatter is as follows. So first of all, for antiprotons, there is a good agreement between the data and the expectation from secondary production, and this allows to have quite a stringent limit on the Einstein cross-section into B bar. And again, it is quite remarkable that current limits allow to probe dark matter particles annihilating into channels of antiprotons with masses up to 1 TeV, okay? Up to 1 TeV, which is quite of a remarkable conclusion. For the positron, the situation is a bit more confusing because there has been this excess in the AMS data and before in the Fermi data and the Pamela data for many, many years, which is now quite robust. And it is unlikely that this excess comes from dark matter annihilations because these positrons will produce a large gamma ray emission, which is not observed, and also because these photons, or these positrons, sorry, will ionize the medium too much, which is not observed by the Planck collaboration. In recent years, also antideuterons are emerging as a promising channel for infrared detection because there is basically no background. This is the background that one has from secondary antideuterons produced by collision of protons and protons, and this is the maximum flux that one allows from dark matter annihilation. So one sees that the search for dark matter in antideuterons is background-free. So this is something which is quite interesting in view of the fact that for antiprotons, for example, for positrons, you have large background, and similarly for the antihelium. Okay, so I don't have so much time left, so now let me mention about the neutrinos. So the neutrino limits are still quite far from the expectation from the thermal production, so clearly this requires new instruments or new targets. And in recent years, active galactic nuclei are emerging as a promising probe for new physics. Okay? So this is due to the discovery by ICHEP a few years ago in 2022 of neutrinos coming from active galactic nuclei from NGC 1068. So this is the idea that the AGN produces protons, they are accelerating the protons collide with photons or with other protons, they produce pions, and then the pions eventually produce neutrinos, which are the ones that you have here. Now, isospin invariants require that you produce charged pions, you also produce neutral pions produce gamma rays, and these gamma rays have not been observed. Okay? It is expected that some of these gamma rays will be absorbed by the dust surrounding NGC 1068, but nevertheless, it is quite difficult to explain this deficit of photons. So it can only be explained if these pions are produced very, very close to the black hole, which is at odds with the possibility of accelerating these protons up to PeV energies if you want to produce eventually TeV neutrinos. So for this reason, it is quite tempting to interpret these neutrinos detected from NGC 1068 as a signal from dark matter. So this faces two challenges. First of all, why the flux is so large, and secondly, why there is no signal from the Milky Way. So since many, many years, it is understood that the growth of the black hole inside the galactic center produces a spike in the dark matter distribution. So the NFW goes with R to the -1, and then if the black hole is growing, then you produce here density which is much more bigger. Yeah? So this is generic for any galaxy. This is theoretical expectation, but the Milky Way is special because the Milky Way has stars, the S stars, which are orbiting very close to the galactic center, and they are bringing energy from the outer parts of the, let's say, of the orbit to the inner parts of the orbit, and this heats up the matter particles, just via gravitational interactions, and this softens the spike. Okay? So this is the resulting distributions of dark matter in NGC68 and in the Milky Way, and it is much, much bigger in NGC68 than in the Milky Way. So you have a large annihilation rate in NGC1068, smaller in the Milky Way. Another question is whether it's large enough to explain the data and whether this is small enough to explain the absence of data from the Milky Way center. And indeed, it happens that for typical values of the cross-section, it is possible to explain the emission from NGC68, and at the same time to explain why there is no emission from the Milky Way center. Yeah? So the point is that now NGC68 and other nearby active galaxies are becoming as potentially interesting targets for indirect dark matter detection. Okay, so I have 1 minute and 13 seconds, so I'm going to be very quick about the direct dark matter searches, this direction of the parameter space. This is a typical strategy. And these are the limits which are produced by experiments from the observation of a signal of dark matter in your experiment. Okay? So here it is a very impressive plot, but it has a small print. The small print is that dark matter has to interact only with a spin-independent interaction. That dark matter couples with equal strength to protons and neutrons, that the local density is 0.3 GeV per cubic centimeter, and that the distribution is given by a Maxwell-Boltzmann, which is truncated at the escape velocity from the Milky Way. So in recent years, people have been analyzing what are the implications for models and for the experiments if some of these assumptions are lifted. If, for example, if one lifts the assumption of the isospin invariance, then one can relax the limit significantly. And if one considers more generic interactions apart from the spin independent, for example, this one, that by the way corresponds to the exchange of a pseudoscalar, then also the limits are much, much weaker. So for the spin independent interaction, the coupling must be 10 to the minus 5 times the Fermi constant. And for this interaction with the mediation of the pseudoscalar, the coupling can be as large as the Fermi constant. Yeah? Okay, so now let me make, in 1 minute perhaps, is that okay, Farinaldo? Okay, thank you. Some comments about light dark matter. So this is a region which is interesting theoretically, but is still uncharted by experiments. And there have been a few ideas. First one is what is called the Migdal effect, that produces, I have time to discuss what is Migdal effect, but it has gained a lot of interest because it was proposed in 1931, and this process was described for the first time this year. Okay? So this has been a hypothesis for many, many years, and now it is solid physics. Now we know it is there, and now people are using that to detect dark matter. And the second possibility is to boost dark matter, in that, for example, via cosmic rays, but also it is interesting to consider some particular models, like semi-annihilations, where two dark matter particles get converted into another matter particle under radiation. So this dark matter particle comes out with a huge kinetic energy, and this allows to overcome the threshold of detection of experiments. So in particular, this allows to increase sensitivity of experiments by many orders of magnitude if the cross-section is in the ballpark of the thermal value. And also, perhaps also, I'm almost finished, but interestingly, it is possible to use neutrino detectors, such as mini-boom as Dion, to detect dark matter, because now, with this large kinetic energy, it is possible to produce nuclear recoils that can be detected by these two experiments. Okay, so I will skip that about the dark matter scattering with electrons. So these are my conclusions. The first conclusion is that the nature of dark matter is unknown. Could it be a classical field? Yes. Could it be elementary particles? Yes. Could it be macroscopic objects? Yes. So over many, many years, people have been proposed very interesting theoretical ideas, and also very smart experimentalists have devised techniques that are reaching the sensitivity to detect dark matter. So it is quite exciting that the discovery of dark matter could be around the corner, or perhaps not, depending on what is the choice of nature in what is the nature of the dark matter. So my last statement is dark matter remains mysterious, and it's necessary to continue exploring new theoretical ideas and more experimental approaches. Thank you for your attention.
Thank you, Alejandro. So we have time for a few questions. Anyone? I can't see it. Yeah, we have one there.
It's on, yeah. So thank you for the talk. So at the end, you leave all of the three and more on the table. What is your personal view of the most likely scenario?
Well, I'm a particle physicist. So my favorite is particle dark matter because both the wave dark matter and the macroscopic objects, they have their own problems. But for particle dark matter, the main mechanism, which is called the freeze-out mechanism, it is already implemented in nature in other contexts. For example, the abundance of primordial elements is dictated by the freeze-out of the neutrons out of the plasma. The CMB is dictated by the freeze-out of the electrons from the photons in the universe. So it is very natural for the particle physicists to think that would be a particle in thermal equilibrium that went away of thermal equilibrium at some point. So it is very, very natural, just from the physical point of view. And from the model building point of view, it is very, very easy to construct a model of dark matter. That is part of the success among particle physicists because you have to put a dark matter particle, a particle which is neutral, a particle which is stable or long-lived, and then it is quite easy that this particle has the correct abundance. So from different directions, I think that particle dark matter is still interesting, and also from the pragmatical point of view, it is also very interesting because it is potentially testable. Okay? So it is not guaranteed the discovery, depends on many, many factors, but it's potentially testable. Thank you for the question.
We have one more question.
Hey. Yeah, I had some. You talked about dark stars. Is it possible that some of the stars that we see now as shining stars have a significant part of their core which consists of dark matter? And how can we rule it out?
All right, very, very good question. That is now a work in progress with Halim Shaikh. And indeed, here the main implication is that the star, in the standard picture, the star is a self-gravitating object. It just gravitates with the effect of the baryons. But now you put also a core of dark matter together with a gas of visible particles, then that includes a new term in your Heisenberg equations. Okay? And then the effect of the dark matter, of the dark star inside of the normal star would be the evolution would be to make these stars to go outside of the main sequence in the Hertzsprung-Russell diagram, and moreover that will make the star to live shorter. Okay? So it has implications, and I will be delighted to talk to you later about this. Thank you. Thank you.
Okay, so time is up. Let's thank the speaker again. Now I'd like to call to the stage Bjorn. Please come in. So Bjorn, now we have a dark matter theory overview. Now we have a dark matter experimental overview. Thanks so much, Bjorn. The floor is yours.
Okay. Okay. Cool. Good. Thank you for the invitation. I want to thank also obrigado to the organizers for this wonderful conference in this beautiful place. And thank you to my previous speaker for providing, of course, all of the theoretical background, because I was speaking mostly about hardware. However, this is an animation, it's not animated, as you just have seen, and I just want to remind you as an experimentalist how privileged we are, because dark matter is such an important thing, right? Dark matter research is about 30, 40 years old, not that old. And for me, always important is this, with all this evidence is different scales, right? The galactic neighborhood, the early universe after the Big Bang, and everything in between. So we know that dark matter is the only theory that can explain the universe in all scales at all times. And thinking about this conference today, we heard this morning about collider physics, where we have now this incredible precision in standard model matter. It's 5%, sure, but I mean, it's an amazing achievement. We have 5 times as more to look for in terms of dark matter. As you know, it's the lambda CDM, and what you will hear later from Scott Doddleson and Marcelle is we still have to look then for 70%. So for all the young people, we have fantastic job security in terms of being physicists, right? We have a lot to discover. And what I will show you today is also how this really has like how vibrant the field is, right? We sometimes set limits and think, oh God, it's a one-way road. No, it took over 40 years for the Higgs, and we still have a lot to go in all of the different frontiers. Now, it's in the name, lambda CDM, cold dark matter, but a part of it, it's not fast, stable, and it has mass. We don't know much about it, so the phase space is gigantic. And this gigantic phase space means that we have this classical WIMP models, which have been our focus over the last decades, which is pretty much familiar particle physics. We just heard about the freeze out. It is still the best dark matter candidate, and I would say fairly well understood also instrumentally in terms of backgrounds. Then the last years coming up is more and more an increasing focus on low mass signatures. On the theoretical side, we made progress with the freeze in, but we also, of course, have amazing progress here in instrumentation. And particular quantum sensing plays here an increasingly strong role, as we'll show you. And finally, I will speak only very briefly about it, is that, of course, at even lower masses, we also have wave-like axion-like particles. And as we see, these scales, they go, of course, it is always scattering that we have. So we go from nuclear recoils to electron recoils to actually at low mass dark matter, we have new type of coherent of dark matter absorption, so to say. Okay, but setting here the stage, what are the key parameters for us? The key parameters is that as Earth rotates around the Sun and the Sun rotates around the galactic center, we are flying through the dark matter halo with about 240 kilometers per second. And if we now assume even an heavy particle WIMP scale, a weak scale dark matter, we have a recoil of keV. That's very low. The standard alpha decay going around us everywhere here is 5 MeV, right? keV is a very low energy scale. And on top of that, we have to find something that happens only a few times per year with an overwhelming background. So our detectors, all of them, have to be sensitive to the smallest energies, and because of the rarity, a part of the sensitivity, they need to be shielded, so we go underground. They have to be ultra clean, meaning the internal radiation has to be as small as possible, and they have to be able to discriminate a signal from the background, because we want to pick out 5 dark matter particles over 1 billion gamma events. You need to be able to do that. Because of that, over the last 30 years, this is what I call a Morse plot of dark matter. We improved by 8 orders of magnitude until about today with different technologies. And my apologies in advance. I will not be able to go through all of that, of course. You don't want me to go through all of that, but I will pick some most recent results and try to guide us along this slope where we are right now in future developments. So this is a plot you usually don't find. I, quote unquote, means my scientist Knut Mora. You can find this, there's a link in the PDF. You can download this. This is the envelope of all the results I consider important for this presentation. And these are all standard spin-independent WIMP-type interactions. So I try not to be baroque, I try not to have too many. Also, thanks to Alessandro, we already have introduced this plot, but actually these are all in the envelope are updated results of the last few months that are fairly new to brand new. Good. Let's start in the middle, the sodium iodide detectors. You probably all heard about the Dama Libra XS 12 to 13 sigma by now, started in 1989, which sparked this very large effort to understand this excess, to exclude it or to confirm it. And there are several sodium iodide detectors worldwide, SABRE north and south, so they're looking for a phase shift on both sides. One's operating cosine, anise, and cosinus, which just recently went online. These are all sodium iodide and PMT based. They're using quantum sensors they have gone beyond this and excluded this access. One new development here, a fairly recent development, is that after Dharma Libra shut off not too long ago, INFN and LGNS took responsibility of the Dharma Libra detectors, and they, together with these collaborations, work on actually verifying or not and to understand these crystals that have been part of this long controversy more in detail. Then the other results here sort of in the middle field I want to mention because they're actually quite important and very innovative and very well could be the future of some parts of the searches. These are the bubble chambers. The PICO experiments uses the traditional particle physics technology with a fluorine compound. And while you just saw the spin-independent plot, particularly because of the unpaired proton spin of fluorine, you get here among the best, two in the future will get the very best spin-dependent dark matter cross-sections. And we see here that this is a picture from just 2 weeks ago. The PICO 500 experiment is being located and being soon commissioned in Snow Lab as we speak. The great thing about these detectors are part of the spin-dependent sensitivity, because a bubble chamber, you can tune the threshold, and you can tune the threshold to be insensitive to ER background, which are the overwhelming background. Even more innovative, there's something called the scintillating bubble chamber, SBC. This is operating at Fermilab. It's a scintillating bubble chamber with liquid argon. And this scintillating bubble chamber will also go in the next year or 2 years underground to Snow Lab. And here the technology is actually able to go beyond the neutrino fork in the relative parts, because this technology is not sensitive in the same way to the neutrino processes. Good. Another important result, which on the spin-independent part is in the middle, but has very important recent results, is DARMIC-M. DARMIC-M uses the skipper CCDs, which have been at Fermilab pioneered, and with oversampling reach a very good sub-EV root mean squares. And they have been recently able to here exclude, to the first time, to reach and then exclude the freeze-in models, which is a great result by itself. This was the demonstrator. They're presently building the full experiment also at Modane. Good. Now let me go to the sort of the 500-pound gorilla in the room, the Noble Liquid experiment, and I'm a member of one of those Noble Liquid collaborations, LZ, just full disclosure. Noble Liquids have traditionally the best sensitivities. The reason is you can scale them up easily, they're very, very clean, they are fantastic scintillators, high light yield, good resolution, and they have the ability to discriminate with, even before any analysis, to 99.5 ERs from NRs. In addition, you create two types of signals, a light signal and a charge signal. The light signal, of course, of the scale of our detectors is prompt. The charge signal takes a few hundred microseconds. This way, with a good few millimeter resolution, you are able to locate the events in the detector. And because liquid xenon, this is most sensitive, if I would have a vat here of liquid xenon and I put in a brick of aluminium, the aluminium would swim on top of it. It's as dense as a liquid, as a metal. And therefore, we can define this fiducial volume, and everything outside gets stuck, and inside we have what we know, as at least today, the radio purist regions. And this leads to this great power, and I want to mention first the liquid argon experiments with Deep 3600 running since some time. They provided the first evidence of B8 neutrino absorption very recently. This is a CC current process. It's relevant for Dune. And they're still running and upgrading. Then DarkSide 20K is being built right now. It looks very much like Proto-Dune. It's the same type of cryostat in Gran Sasso, and they're aiming for hundreds of ton year exposure with expecting to fill by the end, or ready to fill by the end of 2028. And also, of course, the global argon community has plans for the future to even bigger detectors, but they're yet conceptual. This is Argo. Now let's come to the liquid xenon experiments. Panda X, Xenon, and LZ. These presently provide the very best overall sensitivities. This is a plot from LZ where we have the charge signal versus the light signal. And we see these are log scale, so these are orders of magnitude difference, how in this band we have all the backgrounds, and in this violet shaded part we expect the WIMP. And our selection is so low energy that we start to look for 3 photons and 15 electrons. And with this we set the best sensitivity for spin-independent dark matter of about 2 times 10 to the power of minus 48. Amazing sensitivity. Of course, very comparable Panda X and Xenon. But we went even further. We did a low mass WIMP. And there we're starting with 2 photons and 3 electrons as the minimum. It's incredibly difficult. And here the main backgrounds are not even radiative backgrounds, but they are accidentals. And what is happening is here, that at this lowest part, the neutrino fog is higher. So we are starting to eat into the neutrino fog. And the reason, you might have noticed I said fog, then once you reach this neutrino fog, you cannot shield neutrinos, obviously. And therefore, you will see those. But this is not a hard floor like the ground here, but it's a slowly rising fog of discrete processes. So what's actually happening is like, I used to be on colliders, as many of you know. It's like going from E plus, E minus to PP. We reach exactly the same scaling of not being background free anymore. And we could go beyond that with enough work, of course, in the future. But also for us, it provides a great signal, because what we saw just a few months ago, we published, it got accepted 2 weeks ago, that we have 20 events out of about 30 events. And this is an almost 5 sigma observation of this boron 8 flux. This boron 8 is very important for us because, first of all, we have like a signal, we can demonstrate our performance on, we can reach this, but also, for example, here from Xenon, we can make an independent, flavor-independent flux measurement, or here from LZ on the right side, we can measure the weak mixing angle, Weinberg angle at very low momentum transfers. Good. Also, these collaborations, Plus and EXO have come together, and we're working on XLCD, a future 60 to 80 ton detector to go all the way through the neutrino fog. But let's continue to here. As we know, there is this huge dependency of your scattering target, and for very low masses, you just, with a WIMP, if a light dark matter particle scatters of any nucleus, at some point it's like Bambi against Godzilla, it's so light it don't create any significant recoil anymore. So the problem is you need lighter targets, but these targets need to be lighter than a proton. That's pretty difficult to do, and sensors that are able to read out these very small energies. And for this, in this new cryogenic searches, we're really looking for new systems. In addition, dark matter wavelength, as you also just heard, becomes so long that dark matter sees the entire crystal lattice, and not only one particle. So suddenly we're in the realm of condensed matter systems. And these condensed matter systems with the band structure, this is Sapphire with 27 bands, these bands, they actually provide the type of system with the momenta necessary to probe sub-GeV and even sub-MeV and EV dark matter galactically. But as I mentioned, it's a new regime. As a particle physicist, I was not the biggest fan of condensed matter in my undergrad, and now I have condensed matter books on my desk to understand this. And so in this new scale, we have to understand the chemistry, the statistical mechanics, and we have a whole set of new backgrounds that are most likely vibrational. But how do we measure these signals that are far less than an EV? Traditional particle physics has been enabled by ionization, which minimum requires about 1 EV. To go to measure smaller ones, mean a smaller band gap. And so what we do, we have Cooper pairs. And if Cooper pairs are breaking, we have a fraction of a milli-EV of energy being released in quasi-particles. And we're producing many of them at these scales, so we have a very high efficiency. But we need, of course, keep the noise lower than the signal, so we all have to go to millikelvin temperatures. If not, we couldn't see that. And we read this out with quantum sensors. This is the realm of what I will focus on today, Tesseract, Crocodile, and Crest that provide the best sensitivities presently. Crocodile is a small R&D setup we have in Zurich, actually, with superconducting nanowires. They're basically ER only and very clean, and they're very fast. And while we're not a big calibration, because of the excellent resolution, we managed to set some unique sensitivities there. Personally, very excited, Super CDMS is going to start running next week, finally, with detectors optimized for both nuclear recoil dark matter and very low mass dark matter, 22 kilogram. And this will be very exciting that we see them very soon. And Quest, which in some sense with TES has pioneered many of those technologies, they're getting back in the game in some sense, also this summer with having new science on. Very excited. But I want to talk about Tesseract, and again, full disclosure, it's also an experiment I'm very involved in. This is actually here in my lab. In Tesseract, because of these so-called dark backgrounds, we really optimize on discrimination. So we use different type of crystalline structures that have different sensitivity to different dark matter models, as well as to different backgrounds, including even superfluid helium, because, for example, vibrations are very important background for us, and superfluid helium should not respond to vibrations. And we have the currently world's best detectors, TESs, with 1/4 of an EV energy resolution, and with this we set new limits even on the surface in the order of a few tenths of MeV. And we are fully funded, and we are conducting an experiment right now, and in 2029 we'll go, I look at the forward, we go underground in Modan. Good. I was trying to lead you along this envelope of the best sensitivities we have today. I had to show a simple plot or generate a simple plot. But as we have seen, dark matter can be all of those things. And there are so many more possible ways to go forward. And there's this huge amount of experiments, superfluid helium, D-Light, Alicia, Quest DMC, axion searches, let me come back to in a second, directional searches, qubits, MKITs, Sensei, dark matter eyes, experiments to understand systematics. They're all crucially important because this new regime that we're in, we need to understand it, we need to calibrate it, we need to develop the technology, and once we have all of this together, we need to be able to scale this up to do a dark matter discovery. And beyond that, what I was not able to talk about, the axion searches going to even lower masses, which is another big landscape, but as we here, oops, oh, okay, it's not updated, sorry. Here we have the PK-Quinn region we want to reach, and many future experiments that would exclude a large part of this. Good. With 1 minute to spare, coming to the end. So I hope I convinced you this directional dark matter is really healthy and very vibrant field. For the classical WIMP, very often SUSY inspired or LSP-like, we really have running setups that have world-leading sensitivity. They will run for several more years. And we have plant experiments that go all the way to the neutrino fog and beyond. In light dark matter, we will see all few months new limits, and we are becoming very serious about understanding these backgrounds of working together and complete new technologies. Then there are all the complementary searches, and the previous speaker said, no stone left unturned. It could very well be that we stumble here over something. And personally, I love this field because we really have this rich scientific, intellectual, and technical opportunities. We interact with theorists, with condensed matter colleagues, with companies, and can do a lot of progress. Thank you very much.
Thank you, Bjorn. We have time for one question. There, please. There are two. The same place. So we have SIMPs, actually, strong interacting particles there. Two of them, those. I have one more. Okay, but then we are done.
Okay, so maybe I can start. I had the question regarding the SABRE project. Can you comment more on that?
The SABRE project?
Yeah, the status.
So, I know mostly there's very good progress in Stalwell in Australia by SABRE South. They have, I think, most detector conceptualized ready. Believe the sodium iodide crystals are testing in the lab on the surface right now, as well as the underground space is fully secured and also ready to go.
Okay, so they haven't started.
They haven't started yet, no.
Okay, thank you.
Okay, thanks for the very nice talk here in the middle, in the center. So one of the problems, as you mentioned, that the liquid novel experiments will have is related to the, discriminating dark matter and the neutrino fog. Could you comment on the possibility of directionality or their efforts?
Yeah, of course, in an ideal world, directionality is the way to go forward. But we are resource limited, and directional detectors, they have to be necessarily gaseous, because if not, you have a very short recoil. So you need to build something very, very large, very radio clean. And I think there are R&D projects, as you know, but to do something competitive would be prohibitively expensive. Of course, if we see something, then we would have the type of attention and interest to build these things in a competitive way. But beating with a gas and noble liquid is very difficult. It's very difficult.
Thank you.
So we have just one more question where Vito is, and then later we save for go ahead.
Thank you. On slide 8, there was a representation of the neutrino fog that was labeled as from 2021. Has there been no update to the calculation of the neutrino fog?
You mean slide 8, you said? No.
No, not 8.
Wait, now, which I have two neutrino fogs. I have this one,
Yeah, that one.
That's the one.
or the other one.
Well, that one that says,
The new one.
oh, here.
Yeah, I go.
No, you had that one.
This one.
13.
So it's 13. Okay. It's very hard to understand over the AC what you're saying. Sorry. Okay, hit this here.
Yeah. So it says 2021. Has there been no new calculation?
This is the NR neutrino fog. It cuts off about 0.1 GeV. The ER neutrino fog goes further. Yes, but this is ER. But this goes to about, I think, a few keV. Yes.
Okay, so let's thank the speaker again.
So now we move to Jonathan Li Feng, who is going to present Feebly interacting particle searches. Thank you.
You have everything, so to pass and the point. Okay, good.
Wait a few minutes before.
All right, can I begin? Okay, so let me start by thanking the organizers for the chance to come and talk here. I'm going to be talking about feebly interacting particles and especially about the searches for them. So in the last several years, I think it's fair to say that FIPS have moved from the exotica category to really the mainstream of particle physics. You've already seen that earlier today, where people summarizing enormous experimental efforts, ATLAS, CMS, LHCP, have mentioned FIPS searches. Here at ICHEP, these were very well represented in the parallel talks. So there were parallel talks on FIPS from all of these experiments. And that's fairly extensive, far too many to summarize even briefly in this talk. And of course, that's not all. There's also theory work, model building for FIPS, and also the link to cosmology is very strong, so there were many talks about that. And also, there is a lot of activity that was not represented at ICHEP at all, despite the fact that ICHEP is enormous and very comprehensive. So let me first, though, address the question, why is there all this interest in FIPS? So if we were to just take a very high-level view and just plot the particles we know in the interaction strength mass plane, here's where they are. I guess if we can all look at the middle, maybe that works. Maybe it doesn't. I don't see a pointer up there. Does anybody? No? Okay, so, okay, well, there's the particles we know and love, and, particle experiments shine a light from the upper left-hand corner, and so those are, of course, all the particles we've discovered. They're in that corner. Then there's another corner, which is impossible to discover, and all the action of where we want to find new particles, where we have a chance, but we haven't done it yet, is on that diagonal. And so there are basically two other corners, the strongly interacting heavy particles corner, and then the weakly interacting light particles corner, which is, of course, what FIPS are. And so very briefly, I mean, it's obvious in retrospect that we should consider FIPS because they're one of only two opportunities, thank you, discovering new BSM particles. It's also true that because they're way down there at low mass, you can find them at an enormous variety of experiments and facilities. The last slide showed that. And they are very interesting in that they challenge us to use these experiments, these facilities, to the best of their ability to really exploit their full potential to look for these things. So that's one reason I think FIPS have attracted a lot of attention. Another reason is simply that they are motivated by dark matter. So we've heard these beautiful last two talks on dark matter. You can ask what are the properties of a good dark matter candidate, and given the very simple but quite elegant thermal relic freeze-out arguments, you know that this same plane, you can label this as these are regions where there's too little to be dark matter, they annihilate too much to be dark matter, you overclose the universe, and the right amount of dark matter is on this diagonal. And it's this remarkable fact that that diagonal actually corresponds to where experimental searches are now. So the fact that this was a nice place has been around for decades now, the WIMP miracle, urging us to look for WIMPs here. Something that was realized a little bit later, but also now 2 decades ago, is that there's a whole diagonal here, which Jason Kumar and I called the WIMPless miracle, because it's actually quite miraculous too, but there's not a WIMP in it. That entire diagonal has good dark matter candidates in terms of thermal relic freeze-out. And so what we now realize is that cosmologically, at least, FIPS are as well motivated as WIMPs. This was just a zero-dimensional point in this parameter space. There's actually an entire line that you can map out, which has good cosmological motivation. Third, I think another reason that FIPS have attracted so much attention is that they're very, very nicely connected to the central problems of our field. So there are sort of the big 4 canonical candidates of FIPS. These are axion-like particles, dark photon, heavy neutral lepton, dark scalar. Axion-like particles are, pseudoscalars that couple to FF dual, WW dual, GG dual, and also possibly the fermions. These 3 other ones are very interesting in that they are the possibilities that emerge when you demand that the dark matter, the dark sector, interact with the standard model through only renormalizable interactions. Why are we interested in those? Well, renormalizable interactions are not suppressed by a large mass scale, so presumably they're sort of the most promising, largest interactions that you can have with the dark sector. And that means they're both relatively large, so you have a shot at them. And I think this is not usually completely appreciated. It also means they're quite generic. So take, for example, this diagram, which couples a standard model photon to a dark photon and leads us to this whole dark photon category of models. This diagram is going to give you a non-renormalizable or renormalizable term in the Lagrangian, meaning that the particle that is in here, this X particle, can be arbitrarily heavy and still give you this same term. It's not suppressed by the mass of the X. So you can have a gut scale X particle, you can have a Planck scale X particle, and it will generate the same size of an interaction that you expect. It's only a loop suppressed. Which means in some sense, you are probing all the way up to the Planck scale by looking for things like this. And, generically, we kind of expect these sort of things to show up. So the point of this slide is simply that another reason to look for FIPS is they're connected to the central problems of our field. Obviously, axion-like particles, axions are connected to the strong CP problem, dark photons, dark matter. This heavy neutral lepton, also known as a sterile neutrino, is clearly connected to the neutrino mass problem, and the dark scalar modifies the Higgs potential and is clearly connected to Higgs physics and electroweak symmetry breaking. Okay, so what kind of searches have been done? As I said, I can't possibly cover everything that was even covered at this conference, but let me just give you a flavor of some of the really nice new results that came out. So let's start with axion-like particles. So there are many kinds of axion-like particles. They can couple to photons, Ws are gluons, but also they can have fermion couplings. There was a very nice result presented, which is just fresh off, hot off the press, 2607 here, from Bell 2, searching for photon-coupled ALPS. And so the idea is, Bell 2 is, of course, the E plus E minus experiment. You can make a photon and an ALP, which decays to 2 photons. And so you can look for a 3-photon final state, which has 2 photons with an invariant mass of the ALP. And so you can look for bumps in the diphoton invariant mass. And so looking for that and not finding any, you get results like this. So this is the mass of this axion. This is this coupling in inverse GeV units. And you see that the new result actually cuts way down here. All this green stuff is new. And it's actually pushing quite a bit down from where the bounds used to be in the past. So this is this talk of Heidelbach. There were also results presented here on ALP photon, ALP W, all these other ALPs from many other experiments. So I'll refer to these here, Na64, Phaser, BEST3, LHCb, Na62, all had talks along here. And in fact, you see some of these represented here in this plot also, Phaser, Na64, BEST3, CMS Atlas also. So, you know, this is just an example, but maybe some interesting features to note. First of all, there are some gray regions here. These are the ones that are sort of not published by experiments. These are reinterpretations, typically by theorists, of what I call ancient data here. NuCal, E137, LEP2. If you worked on those, okay, sorry, maybe I shouldn't have called it ancient, but it's old data. The colored ones are the new ones that have been spurred by this sort of new interest in FIPS. And these are all since 2019. So all these colored things that I mentioned are actually quite recent. How much has the improvement done? Well, it's sort of, you know, an order of magnitude in G. Is that a lot or not? There's, after all this white space. I would like to emphasize to you that actually that is quite a significant improvement. Many times, most times in these plots, the event rates go as G squared. Sometimes they go even as G to the 4th, which means that, you know, if you're cutting down an order of magnitude in this coupling, that means that there is some point in this parameter space before you started your experiment which you could have seen 100 or 10,000 events, right? Or another way to put it, if it took you 3 years to get the data to get this result, in the first day of your running that experiment, you were already probing new parameter space. So it gives you a feel for sort of how fresh and how promising these sort of searches are, because you're not doing things that have been done for decades. You're really doing new things, and just a couple days of data can actually produce new results. And finally, of course, it's obvious, but let me just say it, you know, you need a lot of experiments to cover this ground, right? There's a lot of different mass ranges, different experiments have different sensitivities. You can't do it with one experiment. Another very popular target is dark photons. So dark photons can be seen, for example, in fixed target experiments and at the LHC through pseudo-meson decay, pions and etas, say, decaying to not a photon and a photon, but a dark photon and a photon. And then the dark photon is now massive, and it propagates and it decays, for example, to E plus E minus or mu plus mu minus. This is actually a very interesting story. In 2023, Phaser and Na62 set the first new limits on this parameter space from the low coupling side since the 1990s. So again, here's the mass, here's the coupling. All the gray stuff is old, fairly old data. And Phaser first pushed into this parameter space. And then Na62, very shortly after, did the same. You can see that down here. And then a new result presented here was the update of the Phaser results using 2022 to 2024 data, which has pushed farther into this parameter space. So now you've, you know, previously this whole region was okay. It's now excluded by the new Phaser results, the Na62 results. Coming in from the top, we expect Bell2 and LHCb to push down maybe a factor of 3. This is a case where the event rate goes as epsilon to the 4th power, so that's a factor of 100 in sensitivity. But that should come down, this sort of forest of constraints. And what I think is very interesting is that, and there are other experiments too, this parameter space back in 2015 or something looked extremely huge, expansive. Who was ever going to cover that? And the answer is, well, we are sort of trying to cover that. We're pushing up significantly from down here, pushing up down from up there, and this parameter space is getting constrained, which I think is quite an achievement. There are, of course, many different gauge bosons one could look for. Let me just give you a feel for one that may be seemingly difficult, just to give you an idea of how innovative people are. Consider a L mu minus L tau gauge boson that decays invisibly to the dark sector. Now, why might you want to do that? Well, if it couples to the muon and it's light, then it could potentially resolve the G minus 2 muon problem. That was an original motivation. Then, of course, that's anomalous. So then you can make it anomaly-free by making it L mu minus L tau. Why L tau? Well, because you're a theorist and you want to make it very hard for experimentalists to have any handle on this. And so you make it second and third generation only. It doesn't have any first generation couplings. And then to make things worse, let's make it decay to invisible stuff. So here you have the production of a new gauge boson which brems off of a muon and decays to invisible stuff. Seems like a complete nightmare scenario to look for this sort of thing. A new result that was reported here was that this gauge boson is actually constrained by Na62 mu. That's a fixed target experiment at the SPS with a very high energy, up to 250 GeV muon beam, also very high intensity. And with their preliminary result in this, again, mass versus coupling plane, they're able to exclude all this. And that's very interesting because this is the place you were supposed to be on if you wanted to sort of impact G minus 2 of the muon significantly. So that possibility is excluded, irrespective of whether G minus 2 of the muon is an anomaly or not. So this was talked about in the Molina Bueno talk. Okay, let me then highlight a few things that I think are very interesting and maybe underappreciated. X17 and the Tomke anomalies. So there is an anomaly in this field of FIPS, which has a very interesting story. In 2015, the Tomke group in Hungary, a nuclear physics group, reported a 7 sigma excess in beryllium-8 decays. So what are they doing? They smash together protons on a lithium foil. They make an excited beryllium-8, which decays to the ground state. Then it can decay radiatively with shooting off a photon. Sometimes that photon pair produces an E plus E minus, and you look for the angle, opening angle of that E plus E minus. And you expect it to drop off monotonically, just because of the virtuality of that photon gets bigger and bigger, but instead you see this bump here. And that is potentially evidence that you didn't just make an off-shell photon, but you actually made an actual real X particle, and you can identify what the mass of the X particle is by where this bump was, and it's 17 MeV. Very interestingly, well, okay, first, I and a group of collaborators showed that you could actually find a solution to this that satisfies all other constraints. It's called the 17 MeV protophobic gauge boson. Very interestingly, a few years later, the Tomke group did this whole thing again with helium-4, found an excess not at 140 degrees, but at 115 degrees, so a different place in the detector. But that's exactly what you expect if you were making a new particle, a 17 MeV particle, because the gap between the excited helium and the ground state helium is bigger than the gap between the excited beryllium and the ground state beryllium. So we have 2 constructively interfering 7 sigma excesses from nuclear physics here. Since then, there's been a 2 sigma exclusion by MEG2, but also a 2 sigma excess seen at 17 MeV by the PADME collaboration. So Andre Frankenthal talked about that in these sessions. So what they do at PADME is they have a monoenergetic positron beam, which hits an electron in matter, and they try to hit the resonance, the 17 MeV resonance, and look for E plus E minus coming out. And here you can see their exclusion, and you see there's a pronounced peak here where you exclude much less than you think right at 17 MeV. So I would say this is a tantalizing anomaly in the field. From my point of view, since G minus 2 is gone, this is the most tantalizing anomaly I think there is in particle physics. It would be great to see what happens. PADME will collect more data, is analyzing more data. There are other experiments finally coming online to weigh in, so I would say stay tuned. Another interesting thing that has emerged and was talked about at these sessions was that there is now the first dedicated LHC search for quirks. So what is a quirk? So you imagine that the dark sector has a strong QCD-like interaction, and it has matter. So the quirks are the matter charged under that dark QCD. Now, if there are no light quirks around, when those quirks are produced, they can't pair produce and hadronize, and so they just oscillate about their center of mass. So this quirk paradigm has massive particles that are 100 GeV-ish with a confining scale, lambda QCD, that's much less than m of 100 GeV. And what you get is particles produced at the LHC that then move around on these non-helical oscillatory paths because they're basically bound together by a color string. If this happens, it depends on what lambda is, but you can have macroscopic oscillations, and it can make it very hard to find these things. So actually, before this work, 50 GeV quirks were allowed. These are 50 GeV heavy, stable, charged particles that are being produced at the LHC in the thousands, and no one has ruled them out. But at this conference, for the first time, quirks were excluded using the phasor experiment, where you look for basically slow particles that come 2 at a time and are out of time with bunch crossings. And that has excluded now this parameter space all the way up to quirk masses of about 180 GeV. So that was Eli Welch's talk. I think there will be many other quirk searches at the LHC after this, dedicated quirk searches. Okay, what's the future in FIPS? Thank you. So at least at CERN, I think there are 2 big things going on. One is the SHIP NA67 experiment. That's been approved. It's a wonderful experiment, fixed target experiment at the SPS, which is planned to start operation in 2033, and there was a nice talk on that by Christian Gianni. The other thing is the forward physics facility, which is not approved. It's a proposed underground detector hall at the LHC. So let me just talk a bit about that. So here's the Atlas IP. This is where phasor is. This is where S&D is. This is the potential site of this forward physics facility out here sort of to the west of Atlas. This is what it looks like in engineering drawings. So this is the surface building. This is this 100-meter shaft to bring it down to the LHC level. And then this is the actual detector hall where you place a bunch of experiments and can look for all sorts of things I haven't even talked about, like milli-charged particles, TeV neutrinos, things like this. This is the surface building design that was presented at the FPF meeting in March. And I just want to give you a feel for the amount of work that's gone to this. Here you see that the engineers have actually decided where to put the fire extinguisher, the anti-panic light, and Wi-Fi. So it's wonderfully detailed. CERN engineers are just amazing. And the point of this is that you could put a bunch of experiments down here to look for particles like quirks, like LLPs, like FIPS, like milli-charged particles. And you could basically very easily scale up the current detectors by a factor of 10,000 sensitivity because they're all about 10 centimeters big. So you just make them 1 meter big in all directions, and that's already a factor of 10. And I haven't even talked about this, but you would detect 1 million TeV neutrinos at this in the high luminosity era. Okay, so let me conclude. There are good reasons, I think, to think that the next breakthrough in particle physics will be the discovery of a FIP. First of all, it's one of 2 possibilities for BSM particles, so you're not really going out on a huge limb to say this. But there are reasons beyond there. The accessible parameter space down here is actually one which is very well motivated by cosmology, by thermal relic principles. It's connected to important problems central to our field, strong CP, dark matter, neutrino mass, electroweak symmetry breaking. And one thing that's really important to emphasize here is that we are really in the low-hanging fruit era of this. There are many opportunities for innovative, fast, cheap, quick experiments to make huge strides. We've seen some of those results presented here already. I think there's many more to come. So thank you.
Thank you, Jonathan. So we have time for a couple of questions. One here on the phone, and there is one on the back over there.
Okay. Thank you, Jonathan. My question is about dark photons.
Yes.
So you're limited yourself by kind of 10 MeV, but I believe that there's a region below MeV, right, where dark photon
Yeah, absolutely.
can be there. So why did you present only by 10 MeV? Is it just
Yeah, basically the answer is for lack of time. But let me just put this up here. So the point is that, dark photons are one incarnation of this FIP, and, they go much, maybe the better slide is this one, sorry. This one. So I'm only plotting from 10 MeV to, 300 MeV here. This is where the new bounds are. This, by the way, is the thermal relic line. And so I'm kind of interested in this area because you have a nice thermal relic density. But absolutely, dark photons could be much lighter. As soon as you get below the 2 electron cutoff, then those things decay to 3 photons. They live an extremely long time, and actually the dark photon itself can be the dark matter. So it's a very interesting part of the parameter space. I didn't talk about it just because of time.
Thank you.
Thank you. There was one on the center, or on the back on the right, over there.
Thank you for the presentation. Could you comment on the situation of stellar neutrinos as candidates to dark matter?
Well, yeah, stellar neutrinos are still a great candidate for dark matter. In the region of, KeV, they're warm dark matter, and that's a perfectly valid possibility. I don't know. There's so much to say. It's hard to know what to think about. I mean, one interesting thing was there was this 3.5 keV line that we had before. I think that's still sort of out there as a possibility, and that could be an interesting signal of stellar neutrino dark matter. But yeah, that's a along with axions and WIMPs, is one of the classic dark matter candidates and still very viable.
Thank you.
So, are there more questions? So one last one here on the. Okay.
Thank you for the nice talk. I wonder about the 17 MeV guy that I know that you are. Is there any way of connecting them, this guy, to some neutrino anomaly or something like this? Something that would also give support for this from the point of view of motivation.
So I don't know that there's a way to connect these two to a neutrino anomaly. There was actually, in some region of this parameter space, there was a way that the protophobic gauge boson could actually soften the G-2 of the muon anomaly. And so that was kind of cool, but apparently now that's no longer necessary, unfortunately. I think the way that people are thinking about it now is, to try to take this apart. So to make this anomaly work, the X boson has to couple the hadrons to basically produce by beryllium 8, but then it also has to decay to E plus E minus. And so, for example, Padme is basically just focusing on this coupling to E plus E minus. It has to couple to E plus E minus. Let's just use that twice by making it made from E plus E minus collisions and then also decay to E plus E minus. And so, in some sense, if you want to say it that way, you can call this Padme result an anomaly, and then those two fit beautifully. I mean, they're at the exact same mass. But yeah, it's bizarre. It's tantalizing and bizarre.
Okay, we have time for one more quick question here.
Yes, thank you. Very, very, very quick question. Can you comment also on the limits from the electron G-2 on the X17 couplings?
X17 couplings. Let's see, do I have that? No, so yeah, there are limits from that on the upper part of parameter space, and the protophobic gauge boson has couplings that are large enough to explain this bump, but small enough to be compatible with those limits. So that was considered. It was actually one of the most stringent, but it's consistent.
Okay, so thank you, Jonathan, again for the nice presentation. And then we go now for a coffee break and resume at 4:10.